Hi everyone. I want to make this little video to help you guys be able to identify functional groups, especially in complex acid and bases, because they will come in very handy when you're dealing with test number 3, maybe answering some questions from test number 2, and some really good review and some skills for test number 1 when you study that for the final. All right. So I'm going to be sharing my screen right here. Right here, you should see the screen. Okay. So we're going to start things off with some acids, okay? The general pattern is that you see a hydrogen that's kind of separated from all the other hydrogens. And if you remember our definition for a Bronsted-Lowry acid, it donates a lone proton being a hydrogen, right? So if right here we have a hydrogen that's separated from all these other hydrogens, and it's kind of safe to say that this lone one's probably going to be protonated. Now that has the hydrogen listed at the very beginning, but a lot of times you'll have hydrogens that are going to be listed at the very end. Now, another way that you can see this being written as is, there we go, CH3COOH, right? Now, the way this is written, you might be thinking, why is this listed that way? It could also be written CO2H, but COOH is something that I hope you guys can pick up on, because if you remember from biology or AP biology from high school, that COOH is a carboxylic acid. And if we were to draw this out, CH3, this is what that carboxylic acid looks like. And you see that for the COOH, you have the C, the first O, which is double bonded to that central carbon. And you have the OH, which is basically the alcohol group for the carboxylic acid. And this is that proton that's going to be protonated. All right. It's being pulled on by a very electronegative atom and a very electronegative system right here. It's pulling that electron density away from that hydrogen. So it's going to protonate very easily. So right here, if we were to rewrite it out, for example, right? CH3CH2CH2OH. Now, you might notice from this compound that the hydrogens are already in multiple places are listed in different spots. Well, if you remember from chapter 1, or not chapter 1, test 1, when you're looking at polar molecules and stuff, hopefully this rings a bell where these are carbon chains. So CH3, CH2, CH2, and then you have that alcohol group right here. And it's that hydrogen in the alcohol group that's going to be protonated because it's not part of that hydrocarbon chain. And again, you have another functional group, an OH, which is an alcohol group. Alcohol is pretty unique because under the right situations, it can also be a base, because that could be an OH2 plus. But for the most part, focus on this. I don't think there's going to be many situations where you see alcohol as a base, especially like with the simplicity with what we're applying for this stuff in general. So for now, if you see that OH, it's more likely going to be treated as an acid. Going over here, let me go to the worksheet. Okay. So let's go over here, because right now we're going to go over some polyprotic things on top of the acids, because on top of complex acids, you also have to be aware that polyprotic acids exist where they protonate multiple hydrogens. And for this, our big one's going to be sulfuric acid, because that is your only strong acid that's going to be polyprotic. It's going to have 2 hydrogens. So right here, sulfuric acid. All right. And you see right here, for each proton that's being lost, you have different Ka values, okay? Excuse me. You have different Ka values for each, because as a compound loses hydrogens, it's going to lose that other hydrogen at a much smaller rate, right? So for example, this anion right here, HSO4 minus. Now, HSO4 minus is not a strong acid. It can protonate, but you still have a negative anion right here and that proton. And if you were to take that proton off, it'd be a 2 minus. So that different dynamic is going to make it a lot harder to remove that second proton. And that goes for subsequent protons. For example, phosphoric acid, H3PO4. If you remember again from bio that or not even bio, semester 1 chemistry, phosphate is one of your polyatomic ions that has a 3 minus charge. It has a 3 minus charge. It has a capacity to be oxidized with a 3 plus charge, and it comes from 3 hydrogens. And phosphoric acid can lose each of those protons. And again, you have 3 different Ka values for each proton right there. 3 different Ka values, and each one of them getting smaller and smaller. Now, the other ones, as you're going through the worksheet, the one that you'll be working with is carbonic acid. And if you remember, carbonate, that's one of your 2 minus polyatomic ions. So it has a capacity to hold 2 protons. So you have H2CO3 and you have HCO3 minus that can act as acids because, again, it can lose both those. Now, for acids that are not polyatomic, there's also hydrosulfuric acid. This is something that you can see where, again, you have a sulfate, or not sulfate, sulfide ion, which is a 2 minus, and it has 2 protons that it can protonate. All right. Another thing to note for acids, something to look out for is, if you remember from test 2, acids are usually correlated with a positive charge. So if you have like NH4 plus, well, has a positive charge. It's not going to really accept another proton and have like a 2 positive charge. It's more likely just going to lose a proton. And I think that might be a good segue to move on to bases, because bases are the complete opposite. Okay, so bases right here, of all the unique bases, one thing that you should probably keep an eye out for that you just have to know off the top of your head is ammonia. Ammonia is NH3. And that is a pretty good base. Not a strong base, but it's still a pretty good one. So when it's protonated, it's going to be NH4 plus, ammonia. And that is its conjugate acid. Another thing that I should probably note is, if you, again, remember from biology, these functional groups, when you have complex organic and biological compounds, one of your most common and best bases is going to be an amine group. If you don't know what I'm talking about, an amine group, let's just do simple this. Amine group is going to be an NH2. That's going to be the same thing, because the NH2 can accept another proton. And when it does, CH3, CH2, NH3 plus. And again, if NH3 plus is your conjugate acid, it has that positive charge, hence is correlated with acids. And that's something that you should also just know and recognize. This NH2, that's going to be your amine group. So it's more likely going to be protonated. And in the converse, on the positive charge, those that are relatively negatively charged are going to be bases, right? Now, if we look at this base right here, okay, CH3, CH2, CH2O, and that corresponds with one of our earlier acids all the way up here. And if we look right here, okay, the minus charge means that it's a base. And if we were to protonate it or add that positive charge, CH3, CH2, CH2OH, which is the same thing as what we had up here. So the positive charge kind of gives us a little hint that it's going to be a base. And right here, we see the regeneration of the alcohol. Another thing that you can see are these ions right here. Because remember, when we're splitting the acid or base in its respective components, if specific components are part of your strong acids or strong bases, then those spectator ions will pretty much not do anything at all with the reaction. They'll be pretty neutral. So the common ones, or the common cations you'll see from strong bases will be potassium, sodium, calcium, magnesium. Those are the pretty common ones. And you might see compounds that are like NaCH3, CH2, CH2O. You see that there's no net charge because the minus charge right here is the counter ion for the plus charge here on the sodium, right? And +1 -1, that makes 0. But again, if we were to do that split, sodium, again, you recognize that it's part of that strong base. So that's going to be pretty neutral because it's a pretty inert spectator ion. But right here, if we were to assign this that positive charge and like remove it because it's that spectator ion, well, where does that leave? A negative charge on this ion. And you know that that's pretty basic. All right. So let's move on down here. Let's just see, these are some of your test questions that may not directly apply to what we just learned, but some really good examples in noticing these kinds of compounds. So for this example right here, it's talking about benzoic acid. And you see again, we have two H's in different spots. This H right here is separated from all the other ones. So that's probably the one that's going to be protonated. And benzoic acid, the compound in real life kind of looks like this. It's again a carboxylic acid. It's not really written that way in this compound, but just the fact that you know that this hydrogen right here is being protonated, you know that it's an acid. It also tells you the Ka, but in all honesty, it could give you the Kb and it could be an acid. That's something you, again, you should really know. Now, let's take a look at this other example. So aniline, right here, hopefully this sparks a little ringing in your head. NH2 is that amine group we were talking about, right? And NH2, if you memorize it, is pretty much a base. So if it's C6H5, NH3 plus, that's its conjugate acid when it's protonated. And again, you see right here, we have a Kb. So it is a base. So hopefully that clears some things up in being able to identify a lot of these things. Here, let me make a quick list of certain compounds you will see. So the ones that we've covered so far, OH, your alcohol, your carboxylic acid, which can be COOH, your NH2, right? And if, again, here, let's just take another step. If NH2 is protonated, there we go. NH2 is protonated, the NH3 plus, or at least that group will, let's pretend like it's connected to another carbon chain. OH, if it was deprotonated, it would just be that O minus. It could be protonated as well, sometimes, not all the time, to H2O plus. And then carboxylic acid, this right here, will be COO. And that'll just be a carboxylate ion. All right. So these are some of the functional groups that I hope you guys can recognize and should be pretty much present in all of these complex biological compounds that you run into in the coming tests, okay? But if you do have questions, please make sure you reach out. Yeah.